In this video, I'm going to do just a bunch of different integrals. I did the problems earlier, and there are different ways that I thought of doing them. I'll explain the ways that I thought of doing them. I've done all of them in advance, so I don't struggle with them while making the video. The idea is, I don't think that does you any good, but I will explain some of the things that I try to do first, and maybe that will give you some insight. So just a bunch of examples of integrals. That's all we're going to be doing here. So for our first example, we're going to integrate sine of 3x times cosine of 2x dx. Now, if you try to let anything be a u or a du, the problem here is that this number and this number are not the same. I mean, you could do a u would be a sine, but then du would still have a 3x locked in there, and there's nothing you can do about that. You can't take the 3 out front, or I mean, you're stuck there. So there's a one special trick that worked for these things, and that was doing the sum and difference of angles. So for instance, we have sine of 3x plus 2x, and the formula for that is sine of 3x cosine 2x plus sine of 2x cosine of 3x. Next we do sine of 3x minus 2x. Now I urge you, always do the bigger minus the smaller one. What you're really looking for here is to get the sine of 3x and the cosine of 2x. So for instance, when I finish this part off, the negative part of that will be exactly this and will cancel out. You'll see. I still have sine of 3x cosine of 2x, but this time minus sine of 2x cosine of 3x. Now I'm going to go ahead and add these two equations together. So this is sine of 5x and this is sine of x. So let me write that on the left. I have sine of 5x plus sine of x equals, now right here, these cancel. Sine of 2x cosine 3x cancels out, and I'm left with what I wanted was the desirable sine of 3x cosine of 2x. And to finish the job, I'm going to divide by 2. So what I'm going to do with this integral then is I'll have a half on the outside, and then I'll have sine of 5x plus sine of x. Each of these are really easy to integrate. Let u equal 5x, and then du will be 5 dx, but you'll divide by 5 to get 1/5. You'll see. Let me write it here. I'll have 1/2, and this. Remember, the antiderivative of sine is negative cos, so I'll get negative 1/5 cosine of 5x, and then over here I'll just get negative cosine of x, and then put a constant at the end. Don't feel a need to go any further. You don't have to simplify anything. None of these integrals ever need to be simplified. In fact, it's probably easier for me to follow your work the more ugly the answer is. The only time simplifying would be necessary is if you're going to use this result in in another problem. There are a variety of ways of starting something like this. I think most people by now will understand that u has got to be something down here. I want my du's to occur on top. Letting u equal x is just nonsense. It doesn't do anything except change the problem to have u's instead of x. So remember that. Write that down. U equals x is always a bad idea. Wouldn't say bad. All right, let me change it. It's always an idea that doesn't do anything. Okay, so you can let u be either that piece or the square root of that piece. I think I'm going to let u equal the square root because I think a good idea, a good practice is to let u be as large a thing as possible to get the job done. Now, there, right here is sort of weird because if I take du, I'll get 1 over 2 radical 4x plus 1, and then I'll get dx. Well, I have that here. The only problem is that between my u and my du, an x never appears. So what we could do is this. To sort of break out of the square root, I can do u squared equals 4x plus 1. Now let me take the derivative of both sides. I get 2u du equals 4 dx. This is beautiful because now I can divide by 4 and change that to u over 2. Now let me go ahead and do the integral. Alright, so this whole denominator is covered by u. The x I can get right here. If I take u squared minus 1, that equals 4x. And then I can divide by 4 to get x by itself. So I'll get u squared minus 1 over 4. And probably not a bad idea here is to take the over 4 and put it out here. Okay, so I've covered this. This is all taken care of. Now what goes into my dx? U over 2 times du. Lots of canceling happens here and some other good, well, this is really nice. The 4 and the 2 can be combined to give me 1 over 8. And then I simply have the integral of u squared minus 1 du. Well, this couldn't be simpler, I suppose. This is 1/8, 1/3 u cubed minus u plus a constant. And then I guess all I have to do now is plug in what u was. U is this radical 4x plus 1, so I get 1/8, 1/3. So I have then 4x plus 1. Well, here it's to the 1/2, and then if I throw this third in here, I'll get to the 3/2, and then I'll have minus the square root of 4x plus 1, or you could write it as to the 1/2 if you want to. And I am perfectly happy with that answer. Don't feel like you have to do anything else with it. Now, I do warn you of this. Most textbooks will put the answer in a more simplified version, so many times you have to make your answer jive with what's in the book. The answer that I saw versus mine was not so much different that I wasn't able to tell that they were actually the same answer. But I think I do cover something where the answers look so wildly different, you need to do some investigation. For a problem like this, I see a number minus a square, so I'm thinking along the lines of cosine or sine, but the problem with that is I can't let x be equal to sine of theta. The reason why, because sine of theta only goes from -1 to 1. X here is unbounded. It can be as high or as low as it wants to be, and only at special places like plus and minus 15 over 4 is this undefined. So sine, since sine doesn't cover all the possibilities of what x is allowed to be, that would be a bad substitution. You could try to let u maybe equal this denominator, but when you take du, you'll get 2x dx, and I don't see an x anywhere around here. So I think, as trig things go, if sine and cosine is not going to work, yeah, you might consider a connection between secant and tangent. We have secant, though, is tan squared minus 1, no, secant squared minus 1 is tangent. And then 1 plus tangent squared is secant. None of these are quite taking the form that I want. However, if you look, 225 is 15 squared, and this over here is 4x, that quantity squared. You should probably know that when you have a difference of squares, it factors readily. So I have 15 squared minus 4x squared. So I'm going to use a difference of squares formula, and I'll get dx all over 15 minus 4x times 15 plus 4x. And you're hoping that this splits up in such a way that you can have it be a over 15 minus 4x plus b over 15 plus 4x dx. So obviously I'm going for partial fractions. Let me go ahead and set up my equation that I'll have to solve. I have 1 over 15 minus 4x times 15 plus 4x equals a times 15 plus 4x. I'm getting ahead of myself, sorry. So anyways, the LCD is this stuff. 15 minus 4x times 15 plus 4x. That is the LCD. So I'm going to multiply everything by that LCD to get the left side just becomes 1. The right becomes a times 15 plus 4x plus b times 15 minus 4x. And there's a bunch of ways that you can go about getting your answers. Probably the easiest is to pick x values that zero out this part and then x values that zero out this part. For example, I could start with, if I let x equal negative 15 over 4, then I'll have a times 0 plus b. That'd be 15 minus 4 times negative 15 over 4. And it looks like from all that I have 1 equals 30b. And so b equals 1/30th. Now let me go back to the defining equation, which was this guy right here. And this time I'm going to try x equals 15 over 4. In that case, I'm zeroing out the b part. And I think you'll find the same situation happens. You'll end up with a equals 1 over 30. So this was a really simple problem. My integral, let me put it back what it was. That was 225 minus 4x squared. That's equal to 1/30th. A was over 15 minus 4x. And then b was over 15 plus 4x. And I'll pull the 1/30th out front. And I'll have 1 over 15 minus 4x plus 1 over 15 plus 4x dx. Now for each of these, I don't know if breaking it up into two integrals will be useful or not, but what I'm going to do for these is I'm going to let u equal 15 minus 4x, and then du will equal negative 4 dx. So I can't always cancel that. I'll put my negative 1/4 here. And I don't know about using u again, but maybe I'll use w. So that'll refer to this one. W will be 15 plus 4x. So that dw equals 4 dx. And like before, I'll cancel out a 4, like so. I'm not going to write everything I want here, but what I'm saying is I have negative 1/4 du over u. So what I'm saying is I have negative 1 over 120. The negative 1/4 will be times 1 over 30, and you'll get negative 1 over 120 ln the absolute value of 15 minus 4x. Let me explain the same thing over here. This bottom will be w, so you'll have dw over w, but in front of it you'll have this 1/4. The 1/4 times 1/30 is 1 over 120. And as before, the dw over w will be ln of the absolute value of w. For those logarithm fans, you may want to combine this and make a shorter answer. Have at it. I do not require that. Well, try as I might, I don't have a formula that works for ln squared. And whenever something like this appears, like ln times ln, something like that, even if I tried this, and then maybe you could play a game like u could be ln of x, and then du would equal 1 over x dx, and then you might let dv equal the other ln of x. And then v, you probably don't know this, but you have to use integration by parts to just get this integral. But I'll write it, just maybe you have it memorized. Alright, so when I do the uv, I don't care how complicated that is. But then, when I do this, multiplied to that, I'll get the x's will cancel. I'll have ln of x minus 1. And that's actually not so bad, but most people don't remember the formula for ln of x, the integral for ln of x. So the reason I'm saying all of this is because I don't think your average student, even a good student, is going to want to go this route. Because I'll have to do another u substitution, or uv, partial fraction, integration by parts, just on this piece again. Let's say I've chosen not to do this method, just because it looks cumbersome. So I'm not left with a lot of choices. I do not want dv to be the whole thing, because that's the integral I'm trying to solve. So I don't have much of a choice here. I'm going to have to let u equal ln squared of x. So I'm going to do integration by parts. U will equal ln of x. I put the square out here just to remind you to use a power rule and then the chain rule to get your du. So I have 2 ln x times 1 over x dx. Now the other piece that was left, dv, was just dx. So then v would equal x. So a lot of nice things happen, as you can imagine. This integral equals x times ln squared of x. And then the x's here cancel. I get minus 2 integral ln x dx. Now, I guess I was wrong. This would not have been bad, because I'm going to go through just as much effort doing it this way. To do this integral here, I am going to use a u and a v, and once again, letting dv equal ln of x is not going to work. So u will be ln of x, du will equal 1 over x dx, dv equals dx, and then v equals x. I advise you not to do this stuff in your head. Put the parentheses and do your due diligence, or you will mess up a negative. I'm telling you right now. Just listen and heed my advice. My uv is x ln x. And then I have a v du is 1, so I have minus just dx. Well, that's the easiest thing in the world to integrate. So I have x ln squared of x minus x ln of x. And then this one, the double negatives will cancel. This will just be an x. And then don't forget your constant. Ooh, looking at my answers. I caught myself. See that? Look at that guy. Did not account for that guy. Let me get that plus out. That doesn't look good. This is one of the problems we did. I'm going to remind you of it. The integral I referred to as annoying. This one that we did, we broke it up like this. U was equal to secant theta, and then du was secant theta, tangent theta, d theta. dv was secant squared theta, d theta, and then v is tangent of theta. So this integral becomes secant theta tangent theta minus the integral of secant tangent squared theta. If you are planning on using integration by parts a second time, I urge you not to now all of a sudden let u equal secant theta tangent, or I'm sorry, dv equals secant theta tangent theta, even though you could do that and let u equal tangent. What you're doing is you'll basically be erasing what you had just done. You'll undo it by reversing what you, obviously that's what you do to undo things, is reverse the steps you did in the first time. Instead, what we're going to do is rewrite the tangent squared, but I'm going to use an identity. And the identity says that tangent squared of theta equals secant squared of theta minus 1. Now let me put back here. On the left we had secant So this, once I make this identity, I multiply through to get the secant cubed. I'm just breaking up the integrals here. And then I have plus secant theta. Notice I have minus secant cubed and I have secant cubed here, so I'm going to add the integral of secant cubed to both sides. This integral you're supposed to know by heart. And then to finish off my answer, I'll divide by 2. The reason for reminding you of this is because I will need it in the next problem. Let me put those around it so I know where to find it, and I'll put some stars here so when we come back we can find the thing. Alright, the reason why I went through all that was for the next example we'll use it. We have the integral of x squared minus 8x dx. Hopefully when you see something like this you'll be inspired to complete the square. That's really what you're going to have to do. Letting u be anything here is almost impossibly useless, because if I let u equal x squared minus 8x, du would be 2x minus 8, and there's no x's anywhere around here. I could let u be the square root of this, but then when I take u squared, I'm going to have u squared and x squared minus 8x. I'm going to have something be the square root of something. That is not at all desirable. So I'm going to complete the square and try to remind you of how that works while I'm doing it. Remember, the game is to take half of the -8, that'll be -4, square it, so I'll get positive 16, but then I'll subtract off 16 so that I don't change the problem. And so I end up with the first 3 pieces are x minus 4 squared minus 16. Now, one of the things that was given in this problem was that x is given to be greater than 8. I think you get away with this, but, well, I think maybe greater than. It depends on if I divide by something. I'll stick to the nature of the problem and not do anything else. All right, now you're in a situation where you have a variable squared minus a number. So I'm thinking secant. So I would let secant of theta equal x minus 4. Let me plug it in and check it. If I have a secant theta here, this becomes secant squared theta minus 16. I need a 16 in front of the secant theta for this to work. So let me put a 4 in front of the secant. And then take the derivative. So I get 4 secant theta tangent theta d theta equals dx. And I just realized x can be anything at once in this scenario. Well, except certain x values make this negative. In fact, if x is around 4, the interior of this will be negative. The problem specified that x is greater than 8. Well, if x is 8, then 8 minus 4 squared is 16. Minus 16 is 0. So as long as x is greater than 8, this piece right here is more than 16. So we're going to have a positive number. That's good because secant itself has a range that goes from negative infinity to negative 1, union 1 to infinity. With the 4 in front of it, it'll go from negative infinity to negative 4, union 4 to infinity. Well, since we only have to cover 8 to infinity, this is good enough. All right, let me go ahead and put my the next steps in there. You got to be careful about when you make a substitution. Make sure that its range matches up. All right, so I will get, in place of x minus 4 squared, I'll get 16 secant squared theta minus 16. And then dx will be 4 secant theta tangent theta d theta. I'll pull the 4 out front. If I take the 16 out of there, that's another 4. So this will take 4 squared. I'll get a 4 from this piece and a 4 from that. Secant squared theta minus 1 is tangent theta. So all of that will come down to secant theta tangent squared theta d theta. That's 16. I'm going to change tangent squared to secant squared minus 1. And this gives me 16 secant theta cubed, secant cubed theta minus secant theta d theta. And now is where I'm going to use that result that I talked about with the secant cubed. I'll put it over here because it looks like it's going to be time consuming. Secant cubed was 1/2 secant theta tangent theta plus 1/2 ln secant theta plus tangent of theta. Then I have this minus secant theta business, so I have minus 16. The integral of secant theta is ln absolute secant theta plus tangent theta. And now I'll put the plus c in since all the integrals are gone. I'll multiply through by the 16. You'll see I'll get an 8 secant theta tangent theta. And I'll also get an 8 ln absolute secant theta plus tangent theta. But look, I have a minus 16 of the same quantity. And it looks like I'm left with 8 secant theta tangent theta minus 8 ln secant theta plus tangent of theta plus c. Now, all I'm left with doing is converting back to x's, as the original problem was in x's. Right here, this is the defining equation. Secant theta is x minus 4 over 4. So secant of theta equals x minus 4 over 4. Now, they told us x was greater than 8. This is the best of all worlds. We're in the first quadrant because everything's positive. So I'm going to go ahead and make up a triangle involving that quantity there. There's my theta. Secant theta is hypotenuse over adjacent, so I can put an x minus 4 over 4. And then this side will be x minus 4 squared minus 4 squared. Or, instead of that, I can put x squared minus 8x. That was the original problem anyway, so that's this length. All right, so my answer is all this business with secant and tangent. So let's put 8 secant theta tangent theta minus 8 ln secant theta plus tangent theta plus c. Let's go ahead and replace each and every one of these. Secant is x minus 4 over 4, so I get 8 times x minus 4 over 4. Tangent is opposite over adjacent, so I get x squared minus 8x all over 4. Secant theta is x minus 4 over 4, and then tangent of theta was x squared minus 8x over 4, plus a constant. You could leave your answer like that, although a lot of people would want to simplify a little bit. I'll get, like, for example, I'll get 1/2 x minus 4 times the square root of x squared minus 8x. And I'll show you what a book did to me for the answer. Pretty sneaky, but it's still not a problem. If you'll notice, they made the 4's disappear. Now, how in the world can you just do that? Well, one of the things, you'll have to remember that this whole quantity here, let me use my cursor. This whole quantity around here, this whole thing here, could be written as one number over 4. Well, if I did that, then I could do ln of the numerator minus ln 4. Or in fact, I would have a plus 8 ln 4. Well, the fact is that's a constant. Any constant you have can be sucked into C, and you can write the same type of an answer. So this answer's as good as this one. They are both correct answers because they differ by a constant. That's important. We reuse C over and over and over again. Every single problem, it renews itself as a brand new C. So honestly, either one of these answers are acceptable. Slow down what I said. Make sure you understand what I said about that. Two integrals are equal if they differ by a constant. That is something that was talked about 100 times in Calculus 1. This is the reason why we put C's on the end of things, because the derivative of a constant is 0. That's why they differ by a constant. They're the same. For the next example, it has a certain look to it to begin with, but I'm not sure all methods are quite the same. What I mean is this. Down here, if you ask me, this is strangely a square that looks like it needs completing. I mean, it's like z squared plus 2z, and then you would add 1 and subtract 1. And I think you could do that, and it wouldn't be that hard to do. But I think it might be a little bit easier to simply let u equal sine of x, because du then is cos of x. So if I let u equal sine of x, try the other method and see if it, I don't think it's going to be that much harder. I think, in fact, it may not. It may actually be equivalent as far as difficulty. For du, I'll get cosine of x dx. So this integral, so all this up here, this is du. That's the whole numerator. So I'll put 1 over. Down here I have u squared plus 2u. And then I have du. So you can see it even more. It's a completing the square type problem, should you want to do that. Or I find it, to be honest, when it presents itself, partial fractions I find to be an easier route. I'm not going to go through all the details like I did before. I'm just going to show you, as you get better at this stuff, you can start to even indicate certain things without much effort. Like that, I just wrote it without looking at anything because I know how this is going to work. Well, that's what I mean. If I go back to reverse myself to get a common denominator, you do the cross multiplication, you'll have u plus 2 minus u. That will give you a 2 in the numerator over that. That's why I put the 1/2 out of here, so that I would ensure that I have a 1 left over. You try to get these numbers yourself. If you set this to a over u plus b over u plus 2, then a will be 1/2 and b will be negative 1/2. If you put these in opposite order, obviously things change. But at this stage, it's simple. ln absolute u minus 1/2 ln absolute u plus 2. And then all I got to do is put u back. U was sine of x. So I have 1/2 ln absolute sine of x minus 1/2 ln absolute sine of x plus 2 plus c. If you want to combine, go ahead. I do not care if you leave it like this. This, there's a bunch of ways to try. I thought about maybe letting u equal e to the t, but then du would be e to the t dt, and I'm not sure what that would do for me, because I don't have an e to the t, although you can multiply and divide by e to the t since it's not 0. I'm going to try off the bat here, I'm going to try u. I'm going to try to do it like the problem I did before that was similar to that, and see if it yields any positive results. So I'm going to have u squared equals 1 plus 4e to the t. Well, let me take the derivative at this stage and see what it does for me. 2u du equals 4e to the t dt. Well, that's related to this right here, isn't it? 4e to the t is right there. Isn't 4e to the t equal to u squared minus 1? Now let me get that u squared minus 1 off to the other side. That's not too bad. Let's go down here and see. Then I'll put the du at the end. I'll have 1 over u. That takes care of all of this piece here. And then now I've got to put my dt in. which is 2u over u squared minus 1 du. Well, that's highly fortuitous. Look at that. And honestly, again, you could use partial fractions, which I think I'm going to do because it's so simple. This, if you'll remember, anything like that factors as u minus 1 times u plus 1 du. And then that, of course, changes to 1 over. Usually you want, I think, the smaller minus what appears to be the bigger du. Let me do it in my head and see what happens. If I take u plus 1 minus u minus 1, I'll end up with positive 2. So I'll have to divide by 2 to cancel that out. Well, that's nice. Those cancel. So ln absolute of u minus 1 minus ln absolute u plus 1 plus a constant. And now let me, you can, if you want to make this, I'll do it one time. I am trying to indicate to you that I don't care if you simplify, but I think I will just to show you that if you want to do this, there's nothing wrong with it. It's just, don't simplify a problem and then make a mistake. Don't get a problem right, then simplify, make a mistake, and then get points taken off because you felt the need to simplify. I hope that doesn't happen to you. So on the top, I have 1 plus 4e to the t, the square root of that minus 1. And then on the bottom, I have 1 plus 4e to the t plus 1. Be careful. A lot of textbooks give answers for something like this where they go and multiply by a conjugate down here and then they clean up a lot up there. Whatever. It's unnecessary. It's just you should be warned because your book may not make determining the answer be very easy. This would seem fairly evident. If I let u equal ln of x, then du is 1 over x. So I could have a u, arc sine of u, du. Let's give that a shot and see what happens. At the very least, it might make life a little bit easier on us. Du equals 1 over x dx. So I am indeed correct. I get u, arc sine of u, du. Now this is rather difficult. Unless you go about using a table, I suspect that I would use integration by parts. And since I don't know the arc sine of u, the integral of it, I'll let that, if you don't mind, I'm going to use w, v, dw, dv, so that I don't use a u again. All right, my w then, I'll use arc sine of u. Then dw is 1 over the square root of 1 minus u squared. dv is u, du, and then v equals 1/2 u squared. This certainly does not seem wonderful. Well, let's write what I have so far and then see. The first thing I'm going to do is take my wv, and I have 1/2 u squared arc sine of u, and then I have minus v dw. Alright, while I complete things, let me go ahead and fill in the x's on the parts that I have finished. At this stage, I think I'm thinking of arc sine. If I let sine of theta equal u, so I'm doing another substitution, then the derivative of that is cosine theta d theta. So I'll have cosine theta d theta, but then I'll have a cosine theta down here. When all said and done, those will cancel. Up here I'll get a sine squared, and I have a formula for that. So that's not so bad. Okay, so we'll do like I said. I'll let sine of theta will equal u, and then cosine theta d theta equals du. So I'll have sine squared of theta up there. And down here I'll have, well, you know the drill. I'll have 1 minus sine squared. That'll be cosine squared, and the square root of that will end up being a cosine of theta. And then I have cosine theta d theta. So cancel those out. And the formula for sine squared went 1 minus cosine 2 theta divided by 2 d theta. So I have 1/2 ln squared x arc sine of ln of x minus 1/4 1 minus cosine of 2 theta d theta. And then I should just copy this stuff and copy this stuff, but or you can't do that on paper, so I guess I'll try to live like a student while I'm doing this problem. Here, when you take the antiderivative of 1, you'll get a theta. And then here, you'll get a sine of 2 theta over 2, but it will be positive. The 1/4 will make that 1/8 sine of 2 theta. And because it will be easier in the end, I'm going to break that up into 2 sine of theta cosine of theta. Theta, if I'm not mistaken, is arc sine of u. So I have 1/2 ln squared arc sine of ln x minus 1/4 arc sine of u plus 1/4 sine of theta cosine of theta. That angle identity went and made the 8 turn into a 4 because there was a 2 that got canceled. Now I'll just start replacing things as I get to it. Now, what was u? The original u, I believe, was ln of x, wasn't it? Yep, there it is, all the way up there. U is ln of x. So I have arc sine of ln of x. Now the theta, sine of theta was what? Sine of theta was u. Okay. So in fact, sine of theta is u over 1 as far as I'm concerned. Sine of theta is opposite over hypotenuse. So sine of theta was u, so that's u over 1. That makes the other side 1, the square root of 1 minus u squared. So the sine of theta, as we already said, was u. And then cosine of theta is adjacent over hypotenuse, so that's just 1 minus u squared. And then u, of course, was ln of x. So I have 1/2 ln squared, ln squared x arc sine of ln x minus 1/4 arc sine of ln of x plus 1/4 u was ln of x times the square root of 1 minus ln squared of x plus c. me get to see if I can circle all that. I guess I will leave on what is a really good example, because I really tried to think of things to do that would make life easier. A lot of students, if they don't see a trig in the problem itself, would just rather not deal with trigonometry. For some reason, it's not a favorite of everybody. I'm not really sure why it's so very useful. However, many students may go and try to do something different, like the following. If you intend to use partial fractions, look at this thing. I'll have a minimum of 3 different partial fractions. This piece right here will not work because it's not a quadratic. Technically speaking, the worst you're ever able to have in a denominator is an irreducible quadratic. This would have to factor somehow into 2 pieces, and it's difficult. Have fun with it if you want to. This piece here would even break up into t squared minus 4 times t squared plus 4. You would have 1, 2, 3, 4, 5 different partial fractions. That means you conceivably have an A, B, C, D, and E to try to figure out. A huge, monstrous task. So I don't like this at all. This is not... I think what I'm going to do is try to think in these terms. Let me put 1 over t. Now, I know that 256 is 16 squared. So I could do t to the 4th squared minus 16 squared. And that might lead me to maybe let a u be a t to the 4th or something along those lines. And I think I might do that. Or what might be better is this. So I might, let's try this here. A better idea would be this. T, if you keep in mind t, by the way, 2 to the 8th is 256. That means t can't be either plus or minus 2, but that's it. T can be any, well, it can't be 0 either. So 0 plus or minus 2 are all out. Anything in between is okay though. So we might do, let's try... Let me try sine of theta. Let me see. I've got variable squared minus a number, so that's a secant type of a problem. So I might do secant of theta equals t. Let's try this. I'll rewrite that. That's not in a good pace. Well, the problem with this particular thing here is that I am only allowed to use thetas where secant of theta actually is positive. But t is not allowed, the only things t is not allowed to equal are 0, plus and minus 2. And outside of completing the square, I'm sort of stuck here. So I hadn't seen this one coming. This was one your book surprised me with. But you're not allowed t. So this is not going to work either. No, keep this in mind. T does not equal 0 or plus and minus 2. any of the trig functions are not going to work unless they cover everything. Now, we could do secant squared. While secant will go from 1 to infinity, the t values can be anything. So I need to find something different than that. Well, the trick, a very good trick, one that I wouldn't have thought of, but maybe you might think of, get rid of this, get rid of this. If I were to let u equal a t to the 8th, for example, or something like that, then du would be 8t to the 7th. So it'd be nice to have a t to the 7th in the numerator. So this is the cute thing that is done here. Here's the original problem. So what I'm trying to indicate is that none of the normal stuff works. That means something off the cuff, something different is what you must do. So what has been done instead is we multiply the top and the bottom by t to the 7th, dt. Well, that is perfect because now I have a derivative type of a thing up here, and I have in the bottom t to the 7th all over t to the 8th times t to the 8th minus 256 dt. Okay, I haven't changed anything. T still can't be 0 and plus and minus 2. I really haven't done anything at all. But now if I let u equal this business, or even u equals this business, it really isn't going to matter. I think I'll let u equal t to the 8th, and then du equals 8t to the 7th dt. And then I can put the 1/8 out front. So now, t to the 8th is u, and then we have u minus 256 du. Now, it's a partial fraction type of a problem should you want to do that. You could also multiply this through and then have a completing the square type of a problem if you wanted to. Anyways, I will do partial fractions, and once again, I'll leave it to you to determine how you want to break it up. Probably, let me see how this works. And then I'll put something out front to fix it. So the way I usually do it, since I've been doing this for so long, is I'm going to have negative u plus u minus 256. So I probably got this messed up. Let me change that to this, and I'll try again. So I have u minus u plus 256. So I've got to also put a 1 over 256 down here. 1 over 2048. This is easy to do. ln absolute u minus 256 minus ln absolute u plus a c. And then where was u all that time? U was t to the 8th. And I guess to finish it off, I can go ahead and put